Hello, I'm Mr. Bob, and welcome to my Geometry Review video series. This video covers Chapter 11, Section 3, entitled Inscribed Angles. By the end of this video, you will have reviewed recent lessons describing inscribed angles. Discussions will include finding the measure of inscribed angles. You will review the Inscribed Angle Theorem and the use of the Inscribed Angle Theorem. Additionally, you will review corollaries to the Inscribed Angle Theorem and then Theorem 1110 regarding angles formed by a tangent and a chord and associated exercises. If you'd like me to cover any of these topics in greater detail, please leave your request in the comment section below. Please subscribe to the channel if you find this video to be helpful. Thank you. Okay, Objective 1A, finding the measure of an inscribed angle. At the right, the vertex of angle C is on the circle, and the sides of angle C are chords of that same circle. Angle C is an inscribed angle. Arc AB is the intercepted arc of angle C. So as you see there, that C, like what they're saying here, is C is on the circle. Where'd my pencil go? There it is. C is on the circle. And these arcs, AC, and not arcs, these chords, AC and BC, intercept the circle opposite the angle, and they intercept it and at a place called the intercepted arc. So where they intercept between those two, A and B in this case, is an arc that's intercepted by the chords associated with angle C. Theorem 11-9 from your textbook on the next slide describes the relationship between an inscribed angle and its intercepted arc. Okay, Objective 1B, it's the second slide in Objective 1, finding the measure of an inscribed angle. Theorem 11-9, Inscribed Angle Theorem. The measure of an inscribed angle is half the measure of its intercepted arc. And what they're saying here, angle B in this case, you see over here is angle B, and we're talking about its angle right here, is 1/2 the measure of AC. Well, AC, the measure of AC is here, and if we know what the size of this arc is, half of that is the size of this angle. And where they get that, the thing that confused me the first time I looked at it was that what this intercepted arc is measured, when we talk about it, it's measured from the center of the circle. So then you have lines here, okay, here out to here, and this angle here is the angle they're talking about when they say that angle B is half this intercepted arc, or half this angle. So this angle is half the size of this angle. Okay? So it says, with Theorem 11-9, there are 3 cases to remember. But we're going to address case 1. The center is on the side of the angle, or on the center is on the center is on the side of the angle. So the center of the circle rides along on that chord, which is actually a diameter. We're going to prove that. You could prove the next 2 and 3 if you chose. I'm not going to do so here. They're exercise 40 and 41 in your textbook. So case 1 is proved on the next slide. Objective 1C, the third slide now, finding the measure of an inscribed angle. So it says, given circle O with inscribed angle B and a diameter BC. Okay, so here we have angle O right here. Where's my pencil? There it is. Angle O is right here, right? An inscribed angle B. Here's the inscribed angle. Right, there's the inscribed angle. And the diameter of BC, okay, that's that one leg of the angle, is this chord, this is a diameter. It says prove that half of B, or that prove that the measure of B, again, we talked about that, the measure of angle B is 1/2 the measure of AC. And as I pointed out in the last slide, that when we talk about half the measure of AC, we're talking about this angle. That's the key to this whole thing. Draw a radius OA. So they've got this radius drawn in. I'm going to draw it in orange, I think. Come on, orange. There you are. I'm going to draw this in orange. Here they've drawn in the radius. And then they say to form this to form isosceles triangle AOB. So A goes from here, A to O to B. So this is an isosceles triangle. These two sides are congruent because they're radii. Okay, and hence angle A, since OA and OB are congruent and make this an isosceles triangle, then it was given that the measure of angle A and the measure of angle B, again, this angle A, no, I can't see that. I'm going back to red, I guess. This angle A and this angle B are equal to each other. Okay, so now if these are equal to each other, this is all kind of almost given stuff. They're saying that the measure of arc AC, that's this one up on the top that we've been looking at, arc AC up here, okay, is equal to angle AOC, right? AOC, that's the measure of this, because we know from a past theorem that the angle O is equal to the chord, AC is equal to the arc, right? The size of AC. They're all equal to each other. And that's by definition of AC. Then it says that angle A plus angle B, so that's our isosceles triangle angles, A and B, are equal to AC. And how are they equal to AC? Because the sum of these two angles, we're going to find angle A plus angle B, due to the triangle exterior angle theorem, okay, those two together is two measures of angle B right here is equal to this angle here, because the sum of these two angles is equal to the exterior angle from our isosceles triangle. So we have a line that goes across. I'll do it in blue. So we have this diameter going across here, and now we have these two angles. Well, they together add to, this is 180 degrees. So what this angle here is what these are not, right? So the complement, or the supplement rather, of this angle here is the angle AOC, and angle AOC is equal to these two angles of the isosceles triangle. So therefore, we can say that angle B is 2 times, right? Because it says right here, angle A plus angle B is equal to AC. So 2B by substitution, instead of saying A plus B, we're going to say 2B is equal to AC. That again is equal to AC right here. And given that, the measure of AC divided by 2, right here, AC divided by 2 is equal to angle B. And there it is given. We have angle B is equal to this, it strikes off this intercepted arc right here. So angle B is half the angle right here that also intercepts and forms AC, okay? So you can use the inscribed angle theorem to find missing measures on circles. So this will maybe become clearer if it's not yet in another slide. But go over this slide a couple times and think about what's being said there if you're having trouble with it. Okay, example 1, using the inscribed angle theorem. So find the values of A and B. Well, A is right out here. You see it out here. Here's A, and here's B, and this angle inside here is B. Right here is B. Okay? And A is this arc PT. That's A out here. They want to know what this is in degrees. Well, it's whatever the arc says it is, okay? So, what do we know? Look at first of all, you look at what we know. We've heard what we know about the inscribed angle theorem, and we now know that we have this angle here, 60 degrees, is equal to 1/2 of the measure of this arc right here. This PQT, this angle here is 60 degrees, and it's 1/2 of the size of this arc. And if it's 1/2 the size of that arc, then it has to be equal to 120 degrees. Okay, so now what do they want to know? They want to know A. Well, A is 100 right over here, 120 degrees. The measure of PQT is 1/2 of PT. And PT is PQT is 60, and that's equal to half of A. Well, if 60 is half of A, then 120 is equal to A. So there we have A. We found A. Then how do we find B? Well, there's probably a couple ways you could look at this, but maybe we should just go ahead and say, well, let's see. We're going to have the angle. Okay, I'm sorry, I had a cough for a second there. So angle PRS is equal to 1/2 of the measure of PS. So what they're saying here is that PRS, okay, that's this angle right here, PRS, and that's angle B. PRS is equal to 1/2 of A by the addition of arc addition postulate, PT plus TS. And we've given to us that TS is equal to 30 degrees. So down here in the equation, angle PRS is equal to 1/2 of the quantity of PT, which is 120 degrees, and TS, which is 30 degrees. So that added together is 150 degrees, and angle PRS is equal to 1/2 of 50 degrees, 150, which is 75 degrees. So you added up these two arcs. They gave you this arc, this 30-degree piece, and then we discovered the size of A in the previous example. You add the two together, angle B is 75 degrees. And again, remember, this is relative to, I'm going to change colors. I'm going to just point this out one more time. Here's the center of the circle. That angle, 75 degrees, is relative to this angle right there. P, whatever that dot is, we'll call it O. POS, right there, POS. I draw that a little straighter, make an angle out of it. So this is 75, this is 150. Okay, but that's this angle here. Okay. Okay, example 1, check your understanding. So they'd like you to do this one, try to do this one on your own. So why don't you just go ahead and pause and take a look at this, and then when you come back, we'll work it together. But before you go, what are they saying? They're saying the measure of angle PQR. So they're looking at this outside right here. They're looking at PQ, R. They gave you that this piece is 60, but it's not going to help you by subtraction or anything at this point. So anyways, think about it for a while. When you come back, then we'll work it together. Okay, I'll assume that you've looked at it, and I'm sure you've all come up with the correct answer. So this is the same problem as before. So what it's just like what we went through the steps. We know that PQT, right here, PQT, out to here, is 60 degrees. And because of that, we know that arc PT, I'll just draw roughly, arc PT is equal to 120 degrees, right? 120, because it's 2 times this angle. This is half this angle out here. So then they gave us the 30. So now you have 120 plus 30 is 150. And then what do they say up in the given? They say find PQR if RS is 60. Well, here's RS down here. RS is 60. So 120 plus 30 is 150 plus 60 is 210. So that means this is 210 to here. It goes all the way around here. So all that's left now, I guess, is this, is kind of this piece back in here, isn't it? So what we want to do is we want to find PQR. That PQR, that's this angle here, and it's going to be equal to whatever this measure is, this total measure out to here. And we just decided that it's 210 degrees. And if you take 210, and that's half of this angle, 210 divided by 2 is 105. So we're going to find that the measure of RS, the arc RS, is equal to 105 degrees. Okay? So let's take a look. Objective 1D. It's our 4th slide in the objective of this section. Finding the measure of an inscribed angle. Let's look at some corollaries. Corollaries to the Inscribed Angle Theorem. Small additions, we'll say. 2 inscribed angles that intercept the same arc are congruent. Right? So that's kind of, we're going to see that, I think, in the next slide. 2 inscribed angles that intercept the same arc are congruent. An angle inscribed in a semicircle is a right angle. And opposite angles of a quadrilateral inscribed in a circle are supplementary. So a quadrilateral has 360 degrees. Making them supplementary would be 180. So angles across from each other are going to be 180 degrees if you to sum them up, right? Okay. So let's take a look at this. You can use the Inscribed Angle Theorem to find missing measures on angles. So let's see what we come up with. Okay. Finding the measure of the numbered angles. Example 2. So what do we have? The measured angle is 1. Right? That's what they want. Or the not measured, I'm sorry, excuse me. The numbered angle. Well, corollary 2 from our list just previously says that an angle inscribed inside a semicircle is 90 degrees. Well, here we've got it. This line right here is the diameter. It goes, as you know, through the center of the circle, creating a hemisphere. So this angle is inscribed within a hemisphere. And if it's inscribed within a hemisphere, that makes this angle 90 degrees. That's by corollary 2. Okay? Now let's look at the other one. Angle 2, it says they want us to find the numbered angle. So now we're looking to find 2. So what is the measure of angle 2? Well, remember we talked about, I think it's the 3rd or 2nd maybe. Maybe it's the 2nd corollary. It says, I don't think it was the 2nd, but maybe it is. If 2 angles, inscribed angles, these are inscribed angles, this one here and this one here, and this angle here too is inscribed, and they come out to a point. Angle 2 comes out and intercepts, the intercepted arc is right here. And this angle over here comes out, it's here and its chord is here, intercepting the same arc. If this is 38 degrees, then angle 2, I'll go up here, 2 is equal to 38 degrees. Because the corollary says if two angles intercept the same arc, then those angles are congruent. Okay, example 2, check your understanding. For the diagram at the right, find the measure of each numbered angle. So why don't you go ahead and try it. When you come back, we'll do them together. Okay, let's assume you've done it, and we're going to look at these. So let's see if we can pick off the easier ones first. We see a diameter between 4 and 2. There's a diameter in our circle pointed out to us. So we're going to use that diameter because Corollary 2, I think it says, that an angle inscribed inside a semicircle, this diameter creates 2 semicircles. Inside a semicircle, that angle is 90 degrees. So that's 1 and 3 are 90. So angle 1 is equal to 90 degrees, and angle 2 is equal to 90 degrees. Now let's do 4. And the reason I say angle 4 is because we have these 2 angles right here given to us. And so we know that angle 4 is 1/2 the sum of these 2 arcs. So, because angle 4 comprises both of these arcs. So if we take 60 and 80 and add them together, so angle 4 is equal to 1/2 60 degrees plus 80 degrees. Angle 4 then is going to be equal to 140. 1/2 of 140 is 70. So now angle 4 we know is 70 degrees. And by Corollary 3, we know that, so angle 2 now, angle 2 is equal to what? We know that angle 3 says that a quadrilateral inscribed inside of a circle, that opposite angles of the quadrilateral are supplementary. Well, we know that 1 and 2 are 90 degrees each, so there's 180 degrees. And we know that 4 is 70, right? So that's all that we can do both ways. We can do the subtraction, or we can do exactly what we're going to do here. If we have 70 here, so if we take angle 2 is then equal to 180 minus 70, and that equals to 110 degrees. 180 minus 70 is 110 degrees. So now we have all 3 of our angles. And if you add it up, you've got 110 plus 70 is 180, and 180 from the other angles is 360. Okay, objective 2, angles formed by a tangent and a chord. In the diagram, B and C are fixed points. Point A moves along the circle, so you could slide it around the circle as you go around, right? That's point A. From the Inscribed Angle Theorem, you know that as A moves, the measure of A remains the same and is 1/2 the measure of BC, right? Because BC, they say, well, I'll do it over here. BC is fixed. The point, they say right here, points B and C are fixed. They never move. Well, that means that that angle here created by this inscribed, right here, by these radii, hopefully I can draw it straight down there. Anyways, you get the picture. Not a very good picture, but you get the picture. That angle right there, BC, is that angle, right? So this never changes. This A is always 1/2 of that. So no matter where we slide A, we could have A up here, right? It would go over to here and down to C. No matter where we slide this A around the circle, it's always going to be 1/2 of BC. And they're kind of trying to show you that A could be down here, or A could be over here. This angle is still the same angle, no matter where you put A on the circle. You slide it all around, it's always going to remain 1/2 of that arc Okay? So theorem 1110 says the measure of an angle formed by a tangent and a chord. Here's our tangent right here, C, the ray C, is half the measure of the intercepted arc. Well, that's what we've been talking about all along. So here's the arc that is struck off by the chord and the tangent, and that's the arc right here. Okay? And that is angle C down here. Angle C is 1/2 of the intercepted arc. Okay, so BDC in this case. It doesn't matter which way you go. It can be, if we're looking at our ray this way, the angle is this way. On this side, here's our angle. So now the arc is this large arc. Oh, my drawing is not very good, but I have a hardest time drawing with this little pen on this pad. But anyways, you get the picture. Maybe I'll do that again just for the fun of it. I'll erase that. Try it one more time. Can I get any better? I'm going to go around here slowly. I go real slow. Yeah. So their angle here, angle C, this is the arc right there. Okay? Inscribed arc. So let's work on one of these and see. It's basically the same as what we've been looking at. Okay, so example 3, using theorem 1110. In the diagram at the right, KJ, the ray, KJ is a tangent to the circle at J. Find the values of X and Y. Well, based on our theorem, 1110, we know that, right here, we know that Q, angle Q, 35 degrees, it intercepts the circle right here, and that is 70 degrees because Q is half of that intercepted circle ray, of the arc, okay? So since it's half, that's 70 degrees, and we want to know what X is. Well, X strikes off that same arc because it goes from L to J to K, right? So that angle there is creating this arc, and they're the same arc. So that makes angle X also 35 degrees. And it says here, X is equal to 1/2 JL. Well, JL is 70 degrees because Q is 35 degrees. And half of 70 degrees, so the measure of Q is equal to the measure of 35. So going to Y now. Y is 1/2 of QJ. QJ, okay, that's this arc right here. Around the top, that's that arc right up here. It's not, there it goes. QJ. And L, or Y in our case, is 1/2 of QJ. And QJ is how much? Well, QJ is equal to half of QL from here all the way around down to the bottom here, QL, that's what they're talking about here, the measure of QL minus JL. J minus from here, I'm going to change colors, minus JL. So we have QL goes all the way around the circle to L, from Q to L. JL goes from J to L, which we know that is 70 degrees, this piece. Well, if this is 70 degrees, this piece here, this is a radius. It goes right through the center of the circle, right? So this is striking off a radius. And that means that this whole this is a semicircle, 180 degrees. So we can now take 100 over here on the side, 180 degrees, and subtract the 70 that we know about, which is the 70 right here. And when we do that, half of that is so that's 110. And when we take half of that, it's 55. So Y is 55 degrees. Okay, example 3, check your understanding. Directions. Describe 2 ways to find the measure of angle QJK using theorem 1110. QJK. Okay, so they want us to look from Q along this angle here down to K, the long tangent. Okay, so there's the angle right there, this angle right through there. So go ahead and give it a shot. They want two ways to get that angle. So I want you to give it a try, and when you come back, we'll try it together. Okay, now that you're back, let's see what we can come up with. Method 1, whatever that's going to be. So I can see, first of all, this QL is a diameter. So that creates two semicircles. And since that's a semicircle, we now know this is 180 degrees, right? We know it's 180. And we also know that this angle inscribed inside this upper semicircle is 90 degrees. I think we maybe have talked about that before, maybe not. 90 degrees because an angle inscribed inside of a semicircle is 90 degrees. So there's 90 degrees. So we've got a part of this larger angle QJK. We have QJL. So we have QJL. Can I write it somewhere? Okay. We have QJL, QJL plus, we're going to have to get LJK. We're going to have to get LJK. Okay. These are angles. Angle and angle. Okay. So what is LJK? Well, we know that LJK is 35 degrees because it's angle X. So we have Q over here, strikes off 35 degree angle over there, which gives us 70 degrees, right, out here. And we know that half of that then goes back to the angle X, which is 40, so, or 35 rather, excuse me. So that's going to be equal to, I'll take it down, angle Q is 90 degrees plus 35 degrees, 35 degrees. And 90 degrees plus 35 degrees is 125 degrees. So that angle, QJK, QJK is equal to 125 degrees. Now let's do it a different way. Well, we can say that we see QJ, this chord kind of strikes off this arc here, okay? And it is the intercepted arc, right, from this angle K way down here. So K comes up and it intercepts our circle right here and gives us this piece here, and that would give us K. So what we really need is the size of this piece. Well, this what is the size of that piece? So for method 2, the size of that piece is QJ, or arc QJ, the arc, is equal to, okay, it's equal to this entire arc around here minus this arc, which we know is 70, or we can just go to the back side and take this arc the other side. We can say it's equal to 180 degrees, which is the arc here, QL from this side, QL, plus the 70 degrees over here that we have, the 70 degrees, created by this 35 degree angle. 180 plus 70 is equal to 250 degrees. And that says then that angle K, or find QJK, okay, so then angle QJK is equal to 250 degrees divided by 2, is equal to 125 degrees. And if I look at them, there's one. They're both 125 degrees. Okay, thanks for working on it.